Hi, everybody. Let's take a look at the fun homework assignment for section 3.3. This is where our derivative rules actually start getting interesting. We're looking at both the product rule and the quotient rule in this section. Now, hopefully you've already watched my video going over where the product rule and quotient rule came from. We'll just be applying them in the problems within this section. So you see my first problem here asked me to look at the function f of x is equal to x cubed times 8x squared plus 1. And of course, the goal is to take the derivative. Now, if I want to use the product rule to take the derivative, then I have to go ahead and say, well, it's the derivative of the first times the second plus the first times the derivative of the second. Now, I said if I want to use the product rule. Now, I do, and I'm supposed to, since they said use the product rule. I could have kind of cheated here and distributed the x cubed through this group and then taken the derivative of that expression, which that would have been an easier method, but we're supposed to show the product rule in these problems. So in fact, let me go ahead and maximize this so you can see the full screen here. Yeah, that'll look better. So when I'm looking at this one, I know that we are trying to take the derivative of this expression. So when I'm taking the derivative, I can say derivative of the first times the second plus the first times the derivative of the second term in the product. When I take the derivative of the first term, I know it's just the power rule. Derivative of x cubed is 3x squared times the second plus x cubed. And then when I look at the derivative of that second term, the only term that has a non-zero derivative is the first one. Derivative of 8x to the second is going to be 16x to the first. You know, derivative of any constant is 0. So now all I need to do is go ahead and simplify out here algebraically. So I would distribute through the 3x squared throughout the first group. That's where the 24x to the fourth plus 3x squared came from. X cubed times 16x is going to give me 16x to the fourth. At that point, I just combine the x to the fourth terms to get 40x to the fourth plus 3x squared. Now, I'll go ahead and just keep my work maximized because the next several problems asked me to do the same thing. They gave me a product and asked me to take the derivative. So for question 2 here, I had 4x squared plus 3 times the exponential function e to the x. Okay, product rule would say I need to take the derivative of the group 4x cubed plus 3, derivative of the first, times the second, plus the first group times the derivative of the second term. Okay, now, when I take the derivative of that group 4x squared plus 3, again, derivative being constant, 0, derivative of 4x to the second is going to give me 8x. So that's the derivative of the first times the second, e to the x, plus the first, my group 4x cubed plus 3, times the derivative of e to the x, but as we know, derivative of e to the x is just e to the x. Now, if you were writing an efficient answer here, you would say, well, John, our first and second term both have a common factor of e to the x. Why, yes, I'll factor it out. Whenever you factor the e to the x out, if you write what's left over in descending power, it's going to be 4x squared plus 8x plus 3, all times e to the x. That would be a fully factored final fantastic form of the final answer. My next problem gave me h as a function of s. And again, of course, it's a product. I had s to the negative 1/2 plus 8s for my first group, times the group 1 minus s to the negative 1 for the second group. So I said, okay, product rule is going to tell me I need to take the derivative of the first group times the second, plus the first group times the derivative of the second group. Now, in showing out that work, the derivative of the first group, everything in here is power rule, guys. So you'd say, well, the derivative of that first term, negative 1 over 2, s to the negative 3 over 2. The derivative of 8s to the first is going to be 8 times 1, s to the 0. So the s cancels out and you just have 8. So all of this is the derivative of the first group times the second, plus the first group now times the derivative of the second. But the derivative of that second group, the 1 has a derivative of 0. The negative s to the negative 1. The negative 1 comes down. It's going to make that positive 1 s to the negative 2. That's where you see where I got my derivative answer over here. Now, from this step to my next line down here, I just did algebra. I FOILed out the first group, distributed the s to the negative 2 in the second term. So I can say, well, when I multiply the negative 1/2 s to the negative 3 over 2 plus 8, when I multiply that all by my 1 here for the first term, I just get that first group out. That's where the first two terms came from. I distributed the 1 to that group. Then if I distribute the negative s to the negative 1, I'll get a positive 1/2 s, and it's going to be to the negative 3 over 2 plus negative 1 power. That gives me negative 5 over 2 power. And then for the last term, you'd have the 8 times the negative s to the negative 1 for minus 8s to the negative 1. In our second group, I'm distributing s to the negative 2 through here. Whenever you multiply s to the negative 1/2 times s to the negative 2, we know that whenever we multiply, we add those exponents. So that's negative 1 over 2, understood to be plus a negative 4 over 2. That's, again, s to the negative 5 over 2. And then I'll have plus 8s to the negative 1. Positive 1 minus 2 gives me the negative 1 power. Now, from this step to my next, I went in and I said, well, okay, I have two terms of s to the negative 5 over 2 power. So I have positive 1/2 plus 1. That's going to give me positive 3 over 2, s to the negative 5 over 2. You can see I combined those terms and wrote it right here. 3 over 2, and then instead of s to the negative 5 over 2, I put it back in terms of radicals. This tells me it's a square root of s to the 5th in the denominator. That's what I did. Square root of s to the 5th in the denominator. And that 5th power can be on the outside like I have it, or on the inside of the group. And that's an s on the inside, not a 5 on the inside. My 5s and s's look too similar. Now, for my other term here, I had the negative 1/2 s to the negative 3 over 2. Well, that's going to be negative 1 over 2 on the square root of s cubed. That's where that term came from. And then the only other term I had was the 8 that I wrote in there. Please notice your minus 8s to the negative 1 plus 8s to the negative 1 just cancel each other out. So this was my nice answer in terms of s. That's my derivative of h with respect to s. Now, in my problem, they asked me to take this derivative answer, and you'll see here, they said, evaluate dh ds such that s is equal to 16. So I said, okay, dh ds evaluated at 16. That's going to give me, when I plug a 16 in here, what I went ahead and did just to make it easier is I took the square root of 16. I said, well, square root of 16 is 4. We're going to be raising that to the 3rd power. And when I raise 4 to the 3rd power, I get 64 times 2. I got 128. That's where this first fraction came from, the negative 1 over 128. Then I go to my second fraction. I can say, okay, you're still plugging a 16 in for s, but the square root of 16 is 4. So that 4 is going to be raised to the 5th power. And then you're going to take that answer and multiply by 2. Well, 4 raised to the 5th power is 1,024 times 2 gave me 2,048 in that denominator. And again, I can't forget I had the plus 8 there. And in fact, I did forget, so I had to go back and white out. You can see that looks a little messy there and there because the ink didn't write over the white out quite as well. But I have to remember to add that 8 to these fractions. Whenever I added these, and I just used my calculator to do it, getting a common denominator of 2,048, I had 16,371 over 2,048, and they do want that exact fractional answer. They don't want any decimal approximations here, which I think is a good thing. Now for my next one, gives me a quotient. So f of x is equal to 3x over 2x minus 9. And then it's wanting us just to evaluate what f prime of x is. Okay, no problem. Now, so I have my original function here, and I can say, okay, the quotient rule. It tells me to take the denominator times the derivative of the numerator. Often I say low d high minus high d low over low low. The denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared. A good way to remember is to always say, well, I know that that denominator is squared, and then the very first thing it does is it goes up and it becomes a factor in the numerator, and you don't take the derivative of it, but then you multiply that by the derivative of the numerator, and then whatever you do here, you do the opposite of here. So here you're taking the derivative of the numerator, so then you say minus the numerator times the derivative of the denominator. Now, in that process, once you get the quotient rule down, then actually taking the derivatives isn't too bad. We know that the derivative of 3x is 3, and we know that the derivative of 2x minus 9 with respect to x is just going to be 2. So my derivatives are really simple in here, just two easy power rules. Once I do that, though, I can't stop. I have to distribute the 3 throughout the first binomial, and then I'll distribute the 2 times the 3x here. I get 6x minus 27 minus 6x. Well, the 6x's eliminate each other, and it just gives me a negative 27 in the numerator over that denominator squared, negative 27 over 2x minus 9 quantity squared, and you can see that that is what they wanted on the achieve. For the next problem here, it's another quotient rule problem. This time they're wanting me to evaluate the derivative at a specific value of t. Well, I have to take the derivative in general with respect to t before I can evaluate it at some specific value of t. So I'm not even worried about that evaluation at t equals -1 in the beginning of the problem. They gave me a function g of t, and they said, well, let's find dg dt. Okay, quotient rule says square the denominator. Bring the denominator up to the numerator times the derivative of the numerator minus the numerator times the derivative of the denominator. Now, in this case, the derivative of the numerator and denominator is the same thing because they only differed by a constant. The derivative of both of them is going to be 3t squared. So you see derivative of t cubed plus 3, 3t squared. The derivative of t cubed minus 3, also the 3t squared. Now, that's a little blurry there. Let me see if I can address that. There we go. Now, whenever I'm looking at this, I'll go in and say, okay, let's distribute that 3t squared throughout the first group. That gives me 3t to the 5th minus 9t squared. And then please, please remember, as you distribute this 3t squared through this group, everything is being subtracted. So I can say, well, okay, when I multiply here, I would get 3t to the 5th, it's being subtracted. When I multiply here, I would get 9t squared, it's being subtracted. So now when we simplify, we see the 3t to the 5ths cancel. Negative 9t squared minus 9t squared gives me negative 18t squared all over my denominator squared. Now this would be my final answer if they wanted dg dt. They wanted dg dt such that t is equal to -1. So all I did was I plugged a -1 everywhere I saw a t. I knew in my numerator it wouldn't change a thing. It's just going to be negative 18. My denominator is going to be -1 minus 3 quantity squared. That's a -4 squared for a positive 16. Gave me negative 18 over positive 16, reduced down to -9 over 8. And that answer was great. For the next problem here. Again, it's a quotient rule problem. I have f of x is equal to 5 over 1 plus e to the x. So I said, okay, in order to do this problem, I'll need to go in and say, I need to take the denominator and square it, then bring that denominator up to the numerator times the derivative of the numerator. In this case, the numerator is just a constant. We know that that derivative in the next step is going to be 0. It's going to make that an entire first term 0. So the denominator times the derivative of the numerator minus the numerator now times the derivative of the denominator. So now when I'm looking at this fraction, I can say, well, I would have my 1 plus e to the x. Why did it become a 0 here? Because the derivative of any constant is 0, and 0 times any group is 0. So your whole first term up there, 0. Now you have minus 5 times the derivative of the group 1 plus e to the x. Well, the derivative of 1 is 0, but the derivative of e to the x is e to the x. So our numerator is just the negative 5 times e to the x, negative 5 e to the x over that denominator squared. And you can see that that's precisely the way I entered it in on Achieve, and it worked just fine. For number 7 here, ooh, more beautiful problem. It gave me e to the x over x to the 7th plus 1. And so just as in the problem before it, I said, okay, it's a quotient. So as in all quotient rule problems, I square the denominator, then I bring that denominator up to the numerator times the derivative of the numerator minus the numerator times the derivative of the denominator. Now, when I'm simplifying this, derivative of e to the x, e to the x. The derivative of the group, x to the 7th plus 1. Well, we know the derivative of the x to the 7th is just power rule. That's where I got my 7x to the 6th from. And of course, the 1 dropped out because the derivative of any constant is 0. So now I can see that, well, hey, my first and my second term in the numerator both have a factor of e to the x. You can and should factor that e to the x out. Whenever you factor out the e to the x, you're going to be left with x to the 7th minus 7x to the 6th plus 1, putting our polynomial in descending order. That's the good notation there. All over our denominator squared. Please notice you never have to physically square out that denominator. It's better left in a group squared format because this is our fully factored final fantastic form of that answer. For number 8. Now, what I did after number 7 is I stopped showing the intermediate steps. So up through problems 1 through 7, I always showed, hey, I'm going to take a derivative here, and then I took it in the next step. I'm going to take a derivative here, and I took it in the next step. The early problems, even with the product rule, I showed where I was going to be taking the derivative. I said derivative of the first times the second plus the first times the derivative of the second. From 8 and on, I just went from here to here. Most of the time, we don't show this step as we do that. You always can, and if you're ever uncertain about anything, you certainly should show that if you need to, but if you don't need to, it's certainly not required. So that's what I did in my number 8 here. You'll see number 8 gave me a pretty easy product rule problem to work. It's asked me to calculate the derivative of a product, so I said, okay, derivative of this product. That's going to be derivative of the first. Derivative of 2x plus 1 is just 2, times the second, plus the first, 2x plus 1, times the derivative of the second. Well, the derivative of x squared is 2x. Derivative of 7 would be 0. So now I've taken my derivative. I cannot leave it in this format, though. I have to simplify. So I distributed the 2 throughout the first group to get 2x squared minus 14. Distributed the 2x in the second group to get plus 4x squared plus 2x. Combining like terms, you got your 6x squared, and then you have plus 2x minus 14. Nice final answer there. Now, number 9 is similar to our quotient rule problems that we had before. Again, what I've done here that makes it look a lot shorter than the ones before is I didn't show that intermediate step of showing where the derivatives are going to be taken. I just went ahead and started taking the derivative. So when I look at this quotient problem, I think, okay, what do I do every single time? I square the denominator. Then I bring the denominator up to the numerator times the derivative of the numerator. So I just looked at that numerator and said, derivative of that numerator would be 2x. Boom. Minus the numerator, x squared minus 49, times the derivative of the denominator. Well, derivative of x minus 7 is 1. Gorgeous. Now, once I have the derivative taken, I just distribute out. Distribute the 2x in this group. I get 2x to the second minus 14x. And then, of course, the 1 doesn't change this group, but you have to remember that entire group is being subtracted. So it's going to be minus x squared and be minus a negative 49, which makes it plus 49. So then I can say, okay, I've got my numerator simplified out. What do I do now? Combine like terms. 2x squared minus x squared is 1x squared minus 14x plus 49 all over that gorgeous denominator of x minus 7 quantity squared. Now, the reason I say that that denominator was gorgeous was because as soon as I did that and I looked at that numerator, I said, ooh, please notice, first term's a perfect square, last term's a perfect square. I bet this is a perfect square trinomial. Oh, it is. Anytime C is half of B squared, you say, well, half of 14 is 7, 7 squared is 49. This is the binomial x minus 7 quantity squared. And then you say, well, that's the same thing as the denominator. So this problem simplified out just to be 1. Now, you could have taken every single solitary bit of the fun out of this problem if you just went back to the first step and said, yeah, John, I'm not going to use quotient rule on this. I'm just going to factor that numerator and call it x plus 7, x minus 7. The x minus 7s factor out, and you're just taking the derivative of x plus 7, which is 1. You could do it that way, but boy, that would just rip all the fun of the quotient rule out of the problem. So I wanted to do it quotient rule, even though I knew from the very beginning of this problem that the answer would be 1, because I knew that this would simplify to be x plus 7, which has a derivative of 1. Now, looking at number 10 here. In number 10, again, they gave me a product rule problem, and it wasn't one that was very bad at all. In order to take the derivative of any product, I say, okay, derivative of the first term, derivative of x cubed is 3x squared. Of course, derivative of 6 is 0. So derivative of the first times the second plus the first term, now times the derivative of the second. Well, derivative of x cubed is 3x squared. Derivative of x is 1. Derivative of 1 is 0. So I can say, okay, I have my derivative taken correctly. Now it's just a matter of algebra. I distribute the 3x squared throughout the first group to get 3x to the 5th plus 3x cubed plus 3x squared. I FOILed out the second two binomials to get my, again, 3x to the 5th plus 18x squared, and then it would be plus x cubed plus 6. Then as a matter of writing it in descending order, I wrote my highest powered terms first, 3x to the 5th plus 3x to the 5th for 6x to the 5th. And then I have my 4x cubed came from 3x cubed plus x cubed. My 21x squared came from the 3x squared plus 18x squared. And then there was only the one constant of plus 6. So that made it pretty nice there. One more problem here, number 11. For number 11, it's asking us to calculate the derivative of y with respect to x such that x is equal to 4. So in other words, take the derivative with respect to x and evaluate it at 4. So I had a pretty simplistic looking fraction or rational function here, y equals 1 over x plus 8. So I knew its derivative, whether I call it y prime or dy dx, doesn't matter. I call it dy dx since that's how they refer to it in the problem. When I take the derivative, I know I square that denominator. Then I bring that denominator up to the numerator times the derivative of the numerator. Derivative of any constant is 0. Then minus the numerator times the derivative of the denominator. Derivative of x plus 8 is 1. So now I can say, okay, that 0 is going to cancel out or make that entire first term 0. 0 times anything is 0. So your entire numerator is just a negative 1. And of course, your x plus 8 is squared in the denominator. So I know I have the dy dx final derivative answer. Now it's just a matter of evaluating that at 4. When you plug a 4 in for x, you're going to get negative 1 over 4 plus 8 squared. That's negative 1 over 12 squared, which is negative 1 over 144. And you can see that that's what I entered in on Achieve. Now, I'll go ahead and break here, and I'll do the remaining 11 problems in a second video for this section. They start to get a little bit more fun. I had a good time working this section, and I hope you will too.